My name is Antti Keurulainen, and the topic of my presentation is amortized experimental design and parameter estimation for user models of pointing. The other contributors of this work and our respective institutions are shown on the screen. In the scenario shown in the image, we see a user interacting with a computer using a mouse and keyboard while an intelligent system observes their actions. The user's case path is displayed in red, mouse movements in black, and the text input in blue. Additionally, a camera captures the user's gaze direction. Intelligent interactive systems have the potential to monitor user behavior through a variety of sensors, such as keyboards, mouse, cameras, microphones, and eye trackers. In our research, we explore effective methods for inferring a user model based on the data collected from these kinds of sensors. The primary concept of our approach is displayed in this diagram. Our method requires an input user model that contains prior distributions over model parameters but has not yet been adapted to individual human behavior. During phase 1, we train an ensemble cognitive model to perform the task considering the distribution of possible parameter values. By sampling these parameter values, we can generate various human-like behaviors from the user model, simulating the space of possible users and the distribution of potential task environments. In phase 2, we train the analyst to design optimal sequence of experiments for estimating the model parameters. This involves randomly sampling simulated users based on the parameter distribution and learning to fit the model parameters to these simulated users' behaviors, ultimately refining the ability of the analyst to conduct effective experiments. Finally, in step 3, the trained analyst could potentially be deployed with human users, conducting experiments and gathering data to generate a fitted model tailored to each individual user's behavior. This phase leverages the computation conducted in phases 1 and 2, allowing for optimal data collection and parameter estimation without causing any noticeable interaction latency for the users. Now, let us take a closer look at the components of this model. This figure illustrates the user model of pointing employed in our research. The model's key assumption is that the control of the movement is computationally rational. In other words, saccade paths and fixations aim to optimize an objective function, such as minimizing selection time, within the constraints of the perceptual and motor system. The eye movement strategies predicted by the model are adaptive consequences of factors like target eccentricity, target size, oculomotor noise, target detection threshold, and perception noise. These interactions result in a multi-step case-based selection process. Two-step selections are typical in humans, but one-step or even 3+ step selections can occur under certain circumstances, such as when dealing with very small targets. Although computationally bounded rational user models can capture behaviors beyond closed-form or rule-based models, constructing and fitting these models to behavior can be challenging and often require vast amount of data from various sensors. Our approach addresses this issue by automating model parameter estimation for 3 pointing tasks, involving the design of an optimal sequence of experimental triers that maximize the relevance of available information. This figure presents the architecture of the analyst. The reinforcement learner's objective is to learn a sequential policy for the control process by interacting with an environment consisting of a sequence of experiments with stochastically sampled parameters. Actions consist of the specification of the experiment denoted by D and an estimate of the model parameters denoted by theta e. The discrepancy function calculates a reward by comparing the estimated parameters to the true model parameters. The memory stores the history of experimental designs and outcomes for a particular user. Our approach is demonstrated through 3 progressively complex models of pointing. In the first study, we apply our approach to a scenario where only summary statistics are provided to the analyst at the end of each episode. The summary statistics include movement time from the beginning to the end of the episode, target location, target width, and the location of the final submovement. Although individual submovements are not observed, the goal is to infer the noise parameter affecting these movements. In study 2, we applied the analyst to a user model of eye movements. Instead of using summary statistics as in study 1, we allowed the analyst to observe the gaze fixations at each step during the episode. In this study, we report the results of the analyst inferring 3 parameters: oculomotor noise, perceptual noise, and movement time intercept. In study 3, we test to see whether the analyst can discover user model preferences while simultaneously inferring all the parameters from study 2. We focus on the speed-accuracy trade-off, which is a significant determinant of how people choose to interact with computers and is readily detectable in behavior. These graphs summarize the results of the study 1. The left panel illustrates the accuracy of movement noise estimations when the user model has low perceptual noise. Below the scatter plots, histograms indicate the design selections made by the analyst, such as the target distance from the origin and the width. In the middle panel, we show the same for user models with medium perceptual noise, while the right panel represents high perceptual noise. The results reveal that for low perceptual noise, experimental designs tend towards higher eccentricities and large targets. However, as perceptual noise increases, the analyst is incentivized to select targets closer to the origin in order to avoid corrupting the data with very noisy observations. This figure illustrates the results of the third study. The upper row demonstrates how the parameters make an identifiable difference in the behavior of the user model. For example, in panel A, the error rate in reaching the target increases when the perceptual noise is increased. Since the noise parameter clearly impacts the behavior, it should be possible for the analyst to infer it. The lower row showcases the scatter plot of the true versus inferred parameters, illustrating the analyst's capability to simultaneously infer all 4 parameters. This figure shows the analyst's distribution of experimental design choices in 2 histograms. We see here that in this case, the analyst always picks the smallest target, but shows a broader distribution of choice of distances. More analysis of this behavior and comparison to other cases is given in the paper. The right panel shows how the system is able to collect more information during each experimental trial, and how the analyst selected experimental designs outperformed the random designs. In summary, study 3 demonstrates that analyst can simultaneously estimate multiple parameters, and importantly, it can estimate both capacity parameters, which are the oculomotor and the perceptual noise, and preference parameter, which is the speed accuracy trade-off from the same experiment. In summary, our research has successfully demonstrated real-time and sample-efficient user model parameter estimation for 3 progressively complex pointing tasks. Our approach, which incorporates learned policies, has been demonstrated to significantly improve parameter estimates when compared to those obtained from random experimental designs. One of the key benefits of our amortized approach is that it trades the high computational cost during training for a fast and data-lean deployment. This means that once the initial computational investment is made, we can efficiently estimate user model parameters with minimal data requirements. Potential interesting future work could include exploring the effectiveness of our approach with human participants and expanding its applications to broader range of SIGCHI tasks, such as menu search, decision-making, and biomechanical control. This concludes my presentation. I would like to thank you for your attention.